Can a system be powerful and still be limited in crucial ways? Deep learning has advanced artificial intelligence in areas such as image recognition, language translation, and autonomous systems. But its limits appear in technical, practical, ethical, and real-world settings that affect how reliably you can use it. The main limits of deep learning fall into several connected areas. These include data dependency, computational cost, interpretability, overfitting, generalization, robustness, and ethical concerns. Together, they shape where deep learning works well and where it struggles. 0, 4, 0, 5. Deep learning models need large datasets to learn strong patterns and avoid overfitting. High-dimensional data such as images and videos increases that need even more. If the data is noisy, biased, inconsistent, or too limited, model accuracy can suffer. Getting enough data can be slow and expensive. Privacy regulations can also restrict access to sensitive data. In supervised learning, labels require major human effort, and inaccurate or inconsistent labels can reduce model performance. Imbalanced datasets appear when some classes are underrepresented. This can bias a model toward majority classes and weaken performance on minority cases. Common responses include oversampling, undersampling, class weighting, and synthetic data generation methods such as Smote and Addison. Training deep learning models often demands high-performance hardware, such as graphics processing units and tensor processing units. That hardware can be costly, and large models also consume significant energy. In real-time applications, complex models may also introduce inference latency. Several techniques help reduce computational cost. Model compression methods, such as pruning and quantization, can shrink model size and speed inference. Low-rank factorization, knowledge distillation, distributed training, and model parallelism can also make large-scale training more manageable. Deep learning models are often described as black boxes because their decision-making is hard to see clearly. Their complexity and huge number of parameters make them opaque. This can reduce trust, especially in critical areas such as healthcare, finance, and law. Interpretability matters because it helps you understand, debug, and improve a model. Techniques such as saliency maps, GradCam, and LIME explain which inputs influence a prediction. Explainable artificial intelligence approaches, including SHAP values, aim to improve transparency without sacrificing accuracy. Overfitting happens when a model learns noise or very specific details from training data instead of the underlying pattern. As a result, it performs poorly on unseen data. This problem is especially likely when model complexity is high or training data is limited or imbalanced. Regularization helps limit overfitting. L1 regularization adds a penalty based on the sum of absolute weights and encourages sparsity. L2 regularization penalizes large weights, while dropout randomly deactivates some neurons, so the model learns more robust representations. Early stopping watches validation loss during training and stops when improvement ends. Cross-validation tests the model across different training and validation splits. Both approaches help check whether the model generalizes beyond one narrow slice of data. Transfer learning uses pre-trained models such as ResNet and BERT as starting points, then fine-tunes them for new tasks with less data and computation. Robustness is a model's ability to maintain performance under difficult conditions. Deep learning models can be vulnerable to adversarial examples, where small input changes cause wrong predictions. They can also fail under noise, occlusions, distortions, or distributional shifts. Robustness can be improved in several ways. Adversarial training exposes the model to adversarial examples during learning. Data augmentation adds variations such as noise or rotations. Robust regularization reduces sensitivity to small changes, and ensemble methods combine multiple models to reduce susceptibility. Training can take days or weeks, especially with large datasets and deep models. Models may also struggle with rare events and edge cases because those situations are often poorly represented in training data. Bias in training data can lead to unfair or discriminatory predictions. Sources include historical bias, sampling bias, and algorithmic bias from model design choices. The effects can appear in areas such as hiring, lending, and healthcare, and they can erode trust in artificial intelligence systems. Bias can be addressed through detection, better training practices, and transparency. Fairness metrics such as disparate impact analysis can help identify problems. Diverse datasets, fairness constraints, and detailed documentation such as model cards can support more equitable systems. Protections include anonymization, differential privacy, and federated learning, which allows training across distributed datasets without transferring sensitive data. Ethical use also depends on fairness and accountability. Systems should treat groups equitably, and developers should be audited and held accountable for unintended consequences. Deep learning can also be misused in deepfakes, surveillance, and biased decision-making, while automation may displace jobs in some industries. These limits appear clearly in real applications. In healthcare, diagnostic systems can struggle to generalize across diverse patient demographics. Autonomous vehicles may fail in unusual weather or unpredictable pedestrian situations. And large language models such as GPT can sometimes produce incorrect or nonsensical outputs. Understanding limits enables responsible AI. Deep learning is powerful, but its limits are just as important as its strengths. You have seen how data needs, computational cost, interpretability, overfitting, robustness, generalization, and ethical risks shape real-world performance. Addressing those limits is essential for responsible and effective use.